Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 10, seminar 1, which signifies our arrival at a juncture in our course that is very important in the study of any vaguely defined layer of mathematics. That juncture is called solving technical problems, and the process of solving technical problems has the following two main purposes or goals. The first purpose of solving technical problems is the integration of potentially dry, detached, and abstract theory into a practical context in such a way that the students who study this or that layer of mathematics, while expanding their own personal web of mathematical knowledge, get to see precisely what the theoretical material or the theory in general that they study has to offer and can do and can achieve. That mutually beneficial process, or the symbiotic relationship between solving technical problems and studying the corresponding theory, creates the motion through the spiral of studying this or that layer of mathematics that is called progress. That, as the joke goes, is opposite of Congress. And in season 1, episode 2, I explained in great detail why that is so. So here, in the lightning round, when we study the initial amount of theory, that initial or basic theory allows us to solve very basic problems. But the very process of solving these basic problems, the way the idea or the theory goes, facilitates a better understanding of the theory that we just covered. And that in turn allows us to go back to the theoretical material and step up the level of perceived complexity, study slightly more advanced theory, and the study of the slightly more advanced theory allows us to take on more difficult problems. And the very process of solving technical problems, when we merge our understanding of the theory and the practical task in hand, is supposed to enhance and deepen the understanding of both the previously studied, the basic amount of theory, and the more advanced layer of theory, and so on this process goes. More difficult problems, more advanced theory, even more difficult problems, even more difficult problems, even more advanced theory, and on and on and on in an infinite loop. That is precisely what generates this magic of motion over the spiral of studying this layer upward, not downward, but upward. The second goal of solving technical problems is to develop and or improve the problem-solving skills in students. And when it comes to solving problems, different mathematicians will have different opinions, which means that your mileage will vary when you ask a mathematician a question, what type of problems I should be solving. Some people will say that if you enjoy the process of solving problems, especially the competitive problems, and if you have a blast doing it, then by all means do so. On the other hand, some other mathematicians will tell you to stop goofing off or goofing around and get on with the serious business of moving the mathematical needle and working towards earning your corresponding degree, whatever you decide to perceive. Here, it should be understood that regardless of your attitude toward problem solving, what you should know is that every problem in mathematics has 2 degrees of freedom, which means that no matter which problem in mathematics we yank out of from the greater mathematical beyond, it will vary over 2 orthogonal parameters, if you will. The first degree of freedom of every mathematical problem is its texture, and the second degree of freedom, or the second orthogonal or independent, if you will, parameter is the objective of that problem. The texture of a mathematical problem shown over here, the texture of a mathematical problem, can be roughly correlated with the perceived difficulty rating of that problem. That perceived difficulty rating can vary from mundane and to some extent boring plug and chug exercise to a problem that is really mathematical in nature, open-ended, where we have to reason from first principles and handcraft an argument by ourselves. That problem could be perceived to be, for example, easy, medium, hard, very hard, 3 asterisk problem, 5 asterisk problem at the end of the textbook, and the research level problems. Now, in general, the second parameter over which every problem in mathematics varies is the objective. And here, when it comes to the second parameter, all problems in mathematics can be somewhat roughly partitioned into 2 very distinct piles or distinct types: a problem to prove and a problem to find, or a problem to compute, or a problem to construct. Now, very pedantically, if we decide to nitpick, of course, this separation is not very clean. It's not a partition. Somehow these problems overlap or intersect. In other words, when we are dealing with a problem to prove, we may have to compute or construct something, and conversely, if we're dealing with a problem to find, or a problem to compute, or a problem to construct, usually somewhere deep in the bowels of that process there's buried at least one proof of something. But in some sense, this is still nitpicking, and in the big scope of things, this is what we have: a problem to prove and a problem to find. And to give you a little bit of taste, here's a typical problem to find. Evaluate this particular improper integral, and over here, when you do that, you will have to deal with the mysterious parameter. It's called a. What is it? A real number. Can it be negative? Can it be positive? Can it be greater than 4? Can it be greater than 3? Maybe it has to be between 0 and 2. Why? The burden of answering all these questions is on you, but here you have to basically evaluate or find the value of this particular object. Similar, a problem to prove could be the following: if f, over here shown over here with the lowercase f, is a single variable, real-to-real function that is continuous where it needs to be continuous, prove that this here improper integral is basically a synonym for this here improper integral. And if you are in middle school or in high school and you do not know anything about improper integrals, then do not worry about it. All you have to grasp right here at this point is that these funny squiggly lines that you see on the left and on the right, they look very similar, but despite their similarity, the things that has to be done with these squiggly lines are very different in their objective. And lastly, before we start deep diving into the process of solving technical problems using the machinery, the theoretical machinery that we have developed so far, it pays to have a clear mental image, or at least the catalog of popular inversions. And all these popular inversions can be found in the pictorial guide in the free PDF file, the link to which is in the comment section to the video. But what I mean here by popular inversions are the inversions of straight lines and circles when the power of inversion is positive, and when the power of inversion is negative. And ideally, if I pull you aside and ask you, in this particular case, if in white on your right is shown the circle of inversion, and in blue we have a given straight line that does not pass through the center of inversion but has precisely two distinct points in common with the circle of inversion, what will the image of that straight line be when the power of inversion is, say, positive? And without missing a beat, you are expected to tell me that this will be a circle that passes through the center of inversion and through precisely two points in common. Also, ideally, you should be able to fairly quickly generate a convincing proof that this is so. The key points you should be able to highlight, and also ideally you should know how to construct the image of this here straight line under the given chosen inversion using the Euclidean tools alone. That's on the one hand. But in a slightly more relaxed setting, for example, if I were to give an examination on the material that we covered, I will not only allow you to bring the cheat sheets that you just saw a few seconds ago, I would encourage you to bring them to the exam and have these cheat sheets right on your desk, front and center, because the ability to be creative, the ability to exhibit your ingenuity and improvisational skills is not in the list, but it is here in the mind of the student. Creative here, not creative. This is just a simple list of things, but the ability to manipulate this material creatively is in you. However, having said that, it still pays to be very comfortable and to be able to zoom through all the popular inversions that you just saw backwards and forwards, just like, for example, a professional musician can zoom through the scales up and down, left and right, over and out. And we will see why that is so in a moment. We live in a free universe, and by all means, you are free to solve the upcoming problems in any which way using the theoretical material that we have developed so far. But after solving a fair amount of problems using the machinery of inversive geometry, I personally identified an overall approach or a heuristic template, a general canvas, following which you may be able to solve the problems that we're about to solve in the remainder of this course. And again, pedantically, I use the word approach because what you're about to see is definitely not an algorithm and definitely not a method. For example, on one spectrum, we have an algorithm, which is a finite description of the steps that are guaranteed to solve the problem and solve the problem correctly. The method sits somewhere in between. It may or may not work. And the approach is a description of again, heuristic template of steps that do not guarantee the production of a solution on the far end at all. There are no guarantees of any kind. But first and foremost, when we take on this or that technical problem, we should understand well the statement of this problem, because unfortunately, quite often students jump into the process of solving a given problem without truly understanding what is required of them. And sometimes they go totally in a different direction, and at the end, they do not solve the problem that was given. So once we understand the statement of a problem correctly and deeply, so that we comprehend 100% what is required of us, then my suggestion is use the following problem-solving approach, which amounts to the following suggestions. First, find a fruitful center of inversion, then find a fruitful radius of inversion, then think about a fruitful power of inversion, and try to also think about the number of inversions that can be applied to the local material. Once you have settled on these choices, the next step in this heuristic template is to invert the local material, in the identified inversion parameters, the ones that were identified over here. Once the relevant objects are inverted, then we move on to the next step, and that step involves solving the inverted problem. And the idea here is that the inverted problem should be easier in some sense than the original problem. And that is the whole point of going through this template. And the point is to arrive at a situation where the original difficult to solve problem becomes easier or more tractable in the inverted state under the cleverly, let's say, chosen parameters of inversion: the center, the radius, the power, and the number, and the composition of inversions. Once the inverted problem has been solved, we move on to the next step in our heuristic template. And that step entails the conversion of the solution of the inverted problem into the solution of the original problem. And as the last step in this template, the suggestion is to write down the forward flow of causality solution steps, because usually when we fight with an interesting and challenging problem, that process is very ugly, it's very messy, it's very hectic. There's a lot of zigs, a lot of zags, dead-end stutters and false starts. But by the time we think that we solved the problem, this last step over here, writing down the coherent and cohesive forward flow of causality steps, allows us to grasp the entire solution at once or at a glance, and thus develop a wholesome understanding, wholesome perception of the solution of our problem. And also technically, what remains outside the frame of this approach that I didn't spell out explicitly is the following two things. First is, in general, many problems that we're about to solve can be solved using the reverse order problem solving approach, where we assume the problem has been solved somehow, and then from that assumption or from the solved state, we try to unwind the steps in reverse order and arrive at the state of the problem. That's the original state, not solved. And then using the insights that we developed into the problem through the analysis of this problem in reverse order, we put precisely the traditional or sought after forward flow of causality or forward order solution steps. That's number one. Number two, this heuristic template that you see over here is a classical embodiment of the transform and conquer problem solving approach. Those of our viewers who are new to this channel, we have studied all these traditional and classical problem solving approaches in a dedicated manner in season 1 and season 2. For example, the transform and conquer problem solving approach, that was the first one we studied. If you missed those, then we recommend that you find season 1 episodes 3 to 7. Across 5 dedicated episodes, we studied this problem solving approach in great detail. You may want to pull up these episodes on our channel, work through them, and get a better understanding of how the transform and conquer problem solving approach works. And in general, this whole template that I have described over here can be collapsed in just 3 basic words: transform, solve, reverse transform. And this is what encoded in this template. And to go over this template with the finer points, the creativity, your ingenuity, your ability to improvise will be hidden or packed precisely in this step right here, during the choice of your inversion parameters. The choices, in other words, the choices that you make here will affect the quality of this step. If the choices that you made are not successful, then after you invert the local material and look at the inverted problem, it will not be easier most of the time, at least initially, and that is fine. We all go through the steps. But if your choice of the inversion material that is packed right here in this process, this right here, series of steps, somewhat rapid, try this, try that, try this, try that. So if your choices here were successful and fruitful, then it is pretty much the miracle of mathematics is that the inverted problem will be easier to solve than the original one. And that is precisely the point, to drive your transform and conquer machinery towards the situation where the inverted problem is in some sense trivial or easier to solve, or perhaps a previously solved problem, in which case, as we studied it on the channel in our dedicated study of the problem solving approaches, is a beautiful combination of reverse order, transform and conquer, and then reduce and conquer. So the whole idea of following this template one more time is to transform the given difficult to solve problem into a situation where the inverted problem is either a previously solved problem or a problem that is easier to solve. And now that you have the description of this template, you will probably come back to this segment in this video many times over, and that is fine. Keep rewinding, keep watching, and let these ideas boil and simmer in your mind. Once they settle, and once you have a better grasp on these steps, then you will be zooming through them without effort, and you will be solving problems using precisely this template. And this is what we will do now. We will take on a very straightforward, in some sense, a trivial problem, and we will see how this approach, this heuristic template, may work in practice. The problem number 11 that we're about to solve will be a sample problem, which will be as simple as possible, but not simpler. Problem for the application of the problem-solving approach that we discussed in the previous segment. And this problem is admittedly contrived, and the whole reason why I put this problem together and decided to make it the first problem is to avoid fighting two battles, because whenever we take on a problem in mathematics, we actually fight two independent battles. The first battle we fight is the battle with the local material, whatever that is, the local lingo. And the second battle is the battle that deals with the method or with the idea or with an algorithm. When we merge these two battles together, then we hopefully take this problem to victory, and that is how we produce a solution of a problem. For example, I do not know, let's say we take on a problem that deals with automorphism group or with kernels of group homomorphisms, for example. Well, in this case, we need to fight two battles, and the first battle that we need to fight is we need to know what the group is, we need to know what a homomorphism or a group homomorphism is, then we need to know what a kernel or a group homomorphism is, and usually it takes its own dedicated amount of time to put the student into a state where he or she knows what these things are. That is one battle. And a totally different battle is the application of some method, if we came up with the method of an idea or maybe even an algorithm that can be laid on top of that local, let's say, group theoretic material. As such, we do not want to fight the fight right now with the local material. We want that material to be as simple as possible, but not simpler. And instead, we want to concentrate all of our energy on comprehending how the problem-solving approach that I just described in the previous segment can be applied to that material and thus solve the problem. As such, in this episode, we will go over all the steps that you saw in the previous template very slowly, very thoroughly, very methodically. But after this episode, I will assume that you know this material better than I do, and I will not stop on all the details. We will just apply this material to the consequent problems right away. And if you think that the problem that we're about to solve is very, very simple, it is, again, for the reasons that I explained. We do not want to fight two battles. We want to fight one battle and comprehend how we can apply the problem-solving approach that I described to these problems. And do not worry, fast enough and soon enough, we will be solving problems that you will have a very rough time solving without this approach and without the machinery of inversive geometry. For example, the problem of so-called chain of Pappus that we will take on very, very soon. I would even argue that you will not be able to solve that problem without the machinery of inversive geometry. In any case, here is the statement of the problem number 11, which again is very contrived, very simple, and a sample problem that we will use as the fodder, as the testing ground for the application of the method or approach that I described in the previous segment. Problem 11 states, construct all circles that satisfy three conditions that are tangent to a given circle, lowercase q, that has the point uppercase Q and the radius r as its radius. These tangent circles must pass through a given fixed, evidently, and coplanar point P that is shown over here, for example, P, and the circles that have their centers precisely on that straight line PQ. Now, it will be very burdensome for me and boring for you to hear the word coplanar all the time, but for now, for the rest, for the duration of this course, we will assume automatically, without me saying that all the objects that we're dealing with are coplanar. They belong to one and the same ambient plane or parent plane, and we will take it as a given fact unless otherwise noted. And it is important to understand that the reason this problem is contrived is because in general this problem is not very interesting if we remove the third requirement over here. If we just say construct all circles that are coplanar, of course, with the material that is given and that touch the circle Q and pass through the point P. There are uncountably, infinitely many such circles. That problem is not very interesting, but to make it interesting, I threw in this extra requirement that the centers of all the circles tangent to the circle Q and pass through the point P must be on the straight line PQ that passes through the given point and through the center of the given circle Q. Based on the possible mutual juxtaposition of the given fixed point P and the given fixed circle Q, we see that this problem has two interesting cases. In the first case, the point P is located strictly inside of the given circle Q, and in the second case, the point P is located strictly outside of the circle Q. And for demonstration purposes, I will go over all the details of the solution of this problem. In the second case, when the point P is located strictly outside of the circle Q, and I encourage our viewers to solve this problem using the machinery of inversive geometry. For the first case, when the point P is located strictly inside of the circle Q, just to test your understanding of the mechanics of the application of the approach that I explained a short while ago. So here, on the one hand, first, we know that this problem is actually less than trivial. We can solve this problem with no effort, pretty much, if we agree that, let's say for brevity, we will name the straight line that passes through the points P, the given points P and Q. We will name that straight line, let's say, lowercase l, and we will designate the two distinct and diametrically opposite points at which the straight line L intersects the given circle Q as, let's say, this will be our point A. Let's say we'll write it down over here, and this will be our point B. Then, without the use of any inversive geometry machinery, how do we solve this problem? Well, this is a trivial case. We bisect the line segment PA, find the center, and snap a circle. That will be the first solution circle that passes through the given point P and touches the given circle Q externally, and will have its center precisely on the straight line PQ as requested over here. And what is the second case? The second case, if we bisect the straight line, the line segment PB, then another perpendicular bisector, obtain the point on the line L, snap another circle that passes through the point P as it is demanded in the statement problem. It will be tangent to the circle Q at the point B. Internally, it will be tangent, and it will have its center evidently on the straight line L. But now, once we understand, and in a very transparent manner, once we understand the solution of this problem by using elementary methods, if you will, we want to obtain the same two solution circles, but using the approach that I described earlier. And to that end, what is the first step? The first step is to find the center of inversion, a fruitful center of inversion. One more time, the reason the approach that I described previously is called an approach, because in the words find a fruitful blah, there is really no algorithmic guidance. Here, our powers of improvisation, ingenuity, and creativity come in. This is where we exhibit them. This is our chance to rise and shine. And here we need to find first the center of inversion. What should it be? Now this, let's go back to the segment where I described the introductory segment to this episode, where I described why we're doing what we're doing. Here it pays to be able to zoom through all the popular inversions, as I said, back and forth, left and right, up and down, and think. If a circle has to pass through the point P, as it is demanded in the statement of the problem, how can we bring the machinery of inversive geometry, the theoretical part that we learned so far? Well, we remember, and this is where, again, your ability to synthesize these things. Any circle that passes through the center of inversion is taken into what? What is it taken to? By an inversion of the parent plane with positive or negative power. It is taken into a straight line, wherever it is, however it is located with respect to the circle of inversion. We don't care. This is the key observation. Any circle that passes through the center of inversion is taken by the corresponding inversion into a straight line, and actually conversely, a straight line is taken into a circle that passes through the center of inversion. And why do we make this observation? Why did we yank this fact out of our web of mathematical knowledge? Well, we yank that fact out of our web of mathematical knowledge because we usually perceive that the fact that the construction of straight lines in vacuum, let's say, even given certain constraint, but the construction of straight lines is a much easier task than constructing circles that honor certain requirements. In other words, a circle is a much more difficult object than a straight line. This is our perception. That is why if we introduce a circle that passes through the center of inversion, we get a straight line, and straight lines are easier to construct. That's the idea. We hope this is where we will gain our tactical win. So what does that mean? That means that we decide on our first step, we decide that The point P, will be precisely our center of inversion. And next, once we settle on the point that will play the role of the center of inversion, we move on to the next step in our heuristic template, where we will think about the radius of inversion. The more problems you solve using the machinery of inversive geometry, the more you will realize that the exact magnitude of the length of the radius of inversion is irrelevant, and as such, in general, as a basic rule of thumb, it is perfectly fine to set the length of the radius of inversion to positive unity, even though you have to be careful, because in some problems, such as the problem known as the chain of Pappus, the exact magnitude of the length of the radius of inversion is what affords a very crisp, elegant, short, and very straightforward solution of an otherwise difficult problem. And once you troll the material of the given problem through this observation, before you commit to the fact that the length of the radius of inversion is irrelevant, you should check if a specific length of the radius of inversion will make your life easier, and that means that you will reduce the number of objects that you have to invert into non-trivial images. In other words, that is the basic rule of thumb. In general, you want to pick such a radius of inversion that will make your life easier, will minimize the amount of non-trivial work that you will have to do, or intuitively speaking, you want to minimize the number of objects that you have to invert into non-trivial images. And as such, in this particular case, it was my decision to pick for the radius of inversion the length of the line segment PA. Remember that the point A is one of the distinct points over which the straight line PQ, otherwise known as L, and the circle Q intersect. And I encourage pretty much all of our viewers to experiment with other radii of inversion. For example, once you walk away from this episode and you work on your own, investigate this problem deeper on your own, I suggest that you try the length of the line segment PB as the radius of inversion and see what happens. And this is exactly the good thing to do, because when you construct different solutions of one and the same problem, that is how you both develop better understanding of the solution of this problem, and that is how you develop a better and deeper understanding of the relevant theory. Now, we will agree that the circle of inversion, which we usually designate with the lowercase c, which is shown in green over here, will have the point P as its center and the length of the line segment PA as its radius, this circle of inversion again shown in green. And now that we took care of two of the parameters of the inversion, the center of the inversion and the radius of inversion, we will move on to the next parameter, which is the power of inversion. In general, the power of inversion that is positive will be more than enough in pretty much all the cases, even though sometimes there do exist problems in which the power inversion that is negative shines brightly and comes in very helpful. We will see that in the problem number 19, the so-called Arbelus and Arbelus encounter. As such, in this particular problem, we choose the power of inversion to be positive, as is shown with the plus sign, plus r square. Remember, to according to our definition, the r square is the power of inversion. We take it to be positive, but again, by all means, we encourage all of our viewers to experiment with the solution of this problem. If the power of inversion is chosen to be negative, see if you can make that case work. But before you do that, we suggest that you comprehend how this problem can be solved by if we assume that the power of inversion is positive. Now that we have settled on the parameters of inversion that we have chosen prior, we'll go through all the local material and carry out precisely that, the inversion of the parent plane with respect to the chosen circle, with the chosen center, with the chosen radius, and with the chosen power of inversion. And remember that initially, at least initially, this is precisely where you will fail several times, many times or not that many times, but this is the place where you will fail. And that is perfectly fine. We all do that when you learn the new material. That is expected. And we also encourage all our viewers not to give up at that point, because during that time when you will be engaging in the cycle of try, fail, try, fail, try, fail, pedantically your mind will be operating in the mode that is isomorphic to the mode in which the mind of a practicing mathematician operates. And that is the whole idea of going through these motions. Prepare yourself for the bigger and better things to come. As such, under the chosen parameters of inversion, we roll through the local material and we invert. The circle Q, the given circle Q with positive power, will be inverted into a pink circle Q prime, and we know that the point A that belongs to the circle of inversion will be what? Stationary or fixed. It will go into itself. It will be taken into itself. But the point B that is located strictly outside of the circle of inversion, will be thrown into the point B prime that is located strictly inside of the circle of inversion. But because the power of inversion is positive, the image points B prime and the pre-image point B will be located on the same side of the center of inversion B. In other words, this step of inverting the local material is shown on the left side of your screen. Circle Q into circle Q prime, point A into itself, point B into point B prime, such that when the line segment B prime A is cut in half, the center of the inverted circle, let's say uppercase Q prime, is located. And now that we have done that, keep in mind the fact that both from the standpoint of all the theoretical and all the practical material that we had developed in the previous 9 lectures, all these steps can be done what? All these steps can be carried out with Euclidean tools alone, according to all the algorithms that are on the books that we presented in the previous 9 lectures. And now that we have obtained the inverted problem, in some sense, our pink circle Q prime shown over here is precisely the inverted problem. We move on to the next step of solving the inverted problem. Now that in the process of solving the given problem using the machinery of inversive geometry, we arrive at the stage of solving the inverted problem, we realize that we score a major tactical win. Why is that? Because we score a major tactical win because solving the inverted problem is not only a previously solved problem, but it is actually a trivial problem as in its own right. Look at this. Given the image of the blue circle Q, the pink circle Q prime, we are tasked with constructing all possible tangents to that circle that pass through which points? Through the points B prime, which is the image of the point B, and through the point A, which is its own image under the chosen inversion with positive power, and so on. As such, it should be evident to all our viewers that this particular task is not only a previously solved problem, because we know how to construct tangents to a given circle through a point that belongs precisely to that circle, but that task using the Euclidean tools alone is in some sense triviality itself, because all we have to do is construct a straight line, such as the straight line T2 and the straight line T1, that is what? That is perpendicular to the given straight line, L, otherwise known as the straight line that passes through the points P and Q, perpendicular to that line through the given point, through the point A and through the point B prime. We know how to do that. This is a trivial task. In other words, our straight lines T1, which is a tangent 1 to the image circle Q prime at the point A, and the straight line T2 for tangent to, or a straight line that is tangent to the circle Q prime at the point B prime, precisely represent the tactical win, and they also represent the solution of the inverted problem, as we highlighted in the description of this approach. And now that we obtained the solution of the inverted problem, we see how many such distinct or unique solutions, if you will, there are or can possibly be. Well, the answer is only two, because through the given points B prime and A, both of which belong to the image circle Q prime, it is possible to construct only two distinct tangents, the tangent T1 and the tangent T2. As such, the inverted problem admits the solution of just two distinct straight lines. Now, why are the straight lines T1 and T2 are also the solutions of the original problem? Well, we answer that question in the next segment, where we convert the solution of the inverted problem into the solution of the original problem. The stage of converting the solution of the inverted problem into the solution of the original problem is usually a lot of fun, because if everything is right and we have made all the right decisions prior, this is precisely the stage when the solution of the original problem emerges, and we gain the sense of intellectual satisfaction because of the work of the job well done. And here, what do we see? We take our straight line T1, that is the tangent to the image circle Q prime at the point A, and we invert it in the circle C, the green circle, with positive power. And we know that according to the corresponding theorem, which I will not name, but I will make it as a fun exercise for you to look up exactly what is the theorem number and where we prove the corresponding fact. But that straight line T1, that is actually tangent also to the circle of inversion at the point A, will be taken into what? It will be taken precisely into the circle, let's say W1. W1, the circle shown in yellow, it passes through the point A, through the point P as was demanded. Its center, uppercase W1, is located precisely on the straight line L, also known as the straight line PQ. And not only that, that solution circle satisfies all the constraints that were stated in the problem. And not only that, we also know how to construct that circle using the Euclidean tools alone, a compass and a straight edge. If you go back to the corresponding theorem, you will see that exactly in this case, we will bisect the line segment PA in half, like this. I do not show it completely, only a little bit of a yellow line, and the intersection of this perpendicular bisector with the straight line PQ will produce the unique point, uppercase W1, which is precisely the center of the first solution circle, W1. Now we move on to the second straight line, the straight line T2, which is a tangent to the image circle Q prime at the point B prime, and the point B prime again is the image of the point B. And according to the corresponding theorem, again, as a fun exercise, as a minor challenge, you guys should look up the number of the theorem. That straight line will be taken, into what? Under the inversion with positive power, it will be taken into the circle lowercase w2, That circle is shown partially, so big it did not fit on my board completely. It runs like so. But not only that, we know how to construct that circle using the Euclidean tools alone. And how do we do it? We go back to our theory, and we still remember that all we have to do is take the point P, the center of inversion, connect that point with one of the points that this straight line has in common with the circle of inversion. See, that one point could be, for example, F2. We call them, or the point F1. It doesn't matter which one we pick. I pick the lower one because there is less material here. We take that line segment, we snap it in half. We construct a perpendicular bisector of that straight line, and that perpendicular bisector will intersect the straight line L precisely at the point uppercase W2, and that point is the center of the second solution circle W2. We put the compass in the point W2, open it up to the distance to the point B, or the center of inversion. Remember the center of inversion. And we snap the second circle, the second solution circle. And why are these circles are the solution circles? Well, because they satisfy or honor all the demands that were posted in the statement of this problem. The first circle is tangent to our circle Q externally at the point A, and it passes through the point B. And the second circle W2 is tangent to our given circle Q internally at the point B. It also passes through the point P, and both of the circles have their centers precisely on the straight line PQ. Now, as I said before, usually when you solve an interesting technical problem, that process is very messy, very chaotic, but eventually, if we emerge victorious in that process, then we have a somewhat sporadic understanding of what we just did. And in order to develop a wholesome view of the solution, we go through that solution in one fell swoop and write down all the steps in the traditional sought after or the forward flow of causality order. As the final step of the heuristic template that I described earlier in this episode, we eliminate the potential fragmented understanding of the solution of this problem and replace that fragmented understanding with a wholesome view by listing all the steps, all the solution steps of this problem in the traditional, requested, or sought after forward flow of causality order, or in some sense, we prepare our solution for a publication in order to share our solution and in order to share our ideas with the like-minded individuals. As such, as the step number one, we construct a straight line, lowercase l, through the given points P and Q. The straight line L through the given points P and Q. That straight line L will intersect the given circle Q at two distinct and diametrically opposite points A and B. A and B. Next, as the step number 2, we reflect the given circle Q into its image Q prime with positive power in the circle lowercase c that has the point P as its center and the length of the line segment PA as its radius, P as its center, PA as its radius. This inversion circle is shown over here in green, lowercase c. As a step number 3, we construct a straight line T1 that is orthogonal to the image circle Q prime at the point A. That straight line is shown in pink over here, T1. This is the solution that can be carried out with Euclidean tools alone. We know how to do that. This is a previously solved problem, and it is a trivial problem because we know how to construct straight lines that are tangent to a given circle through a point that is located on that circle. As a step number 4, we construct a straight line T2 that is orthogonal to the image circle Q prime at the point B prime. That straight line is shown over here, also a trivial task. We know how to do it. And that straight line T2 will have two distinct points in common, the point F1 and the point F2, with the circle of inversion shown in green. See, we will need these points later. As the step number 5, we reflect the straight line T1 with positive power into the first solution circle, lowercase w1, via the inversion of the parent plane with respect to a circle, lowercase c, that has the point P as its center and the length of the line segment PA as its radius. And as the solution, as the final step, number 6 in our forward flow of causality solution, we reflect the straight line T2 with positive power. Again, into the second circle, the solution circle W2, lowercase w2, in the same circle C that has the point P as its center and the length of the line segment PA as its radius. As such, we claim that the solution set of this problem contains two distinct circles, the circle lowercase w1 and the second circle lowercase w2. The first circle is shown over here. It passes through the point, given fixed point P, touches the given circle externally at the point A, and has the center, uppercase W1, on the straight line PQ as demanded. And the circles, and the second circle, lowercase w2, is shown over here. It passes through also the point P. It has its center, uppercase W2, on the straight line PQ, and touches our given circle Q internally at the point B. Now here, just to make sure that all our viewers comprehend what just happened in the big scope, from the big perspective standpoint, forgetting all the details, basically we took our original circle, and instead of constructing circles that are tangent to it, which is a difficult problem, we reflected that circle into its image, pink circle Q prime. But here the reflected problem was much easier to solve because there exists only one unique straight line that is tangent to a given circle drawn through a point on that circle. And because we have precisely two such points, only point A and only point B, these are the two solutions of the inverted problem. And once we invert this new material back in the circle, we obtain the image of the circle Q prime will be the original circle Q, and we obtain the two solution circles W1 and W2. Now, in conclusion, if you understood what transpired in this episode, I recommend that you do two things. First, you try to construct a similar demonstration problem that you can give to your students, that they can try their hand and test their hand on applying this material to your problem, and so that they do not get bogged down with other more technical details. And number two, if you think that you understood everything that transpired in this problem, think about the problem that we will be solving in the next seminar. And in the next seminar, we will be given two distinct circles, circle 1 and circle 2. We will be given a point that is located outside both of the circles. And the challenge will be here also to construct all coplanar circles that are tangent at the same time to both of the given circles. And these circles have to pass through that one point. If you have any questions, then the comment section is open. By all means, do ask. Maybe you have to watch this episode several times. Let the ideas simmer and boil in your mind. Once they reconcile in your mind, you can move forward. And also, it may be helpful for you to find on this channel, if you are new to our channel, find the season 3 episode 1. This is the episode, watch this episode, because in that episode I index all the problem-solving approaches that we studied in a dedicated manner: transform and conquer, reverse order, scope expansion, scope reduction, equation, mathematical equivalence, divide and conquer, eliminate and conquer, and so on. And all this information should be helpful. Now, this is it for episode 10, and I will see you next time in the episode 11, in which we will solve precisely the problem that is shown on the right side of your screen.